So how do we graph a logarithm function? Well, we remember that a logarithm is the inverse of an exponential, and we're fairly comfortable, maybe, of graphing an exponential, then maybe we can use that relationship to our advantage. So let's go ahead and look at some test points of this particular value here. So x and f of x. So let's try some values. Let's try if it's -2, -1, 0, 1, and 2. I think those are some good values here. Not really a good table. Let's try the table. Let's maybe solid lines. So if x were -2, what is my valuation of that? That'd be 2 to the -2, which is a 1/4. If it was to the -1, a 1/2. 2 to the 0 is a 1. 2 to the first is a 2. And 2 squared is a 4. So we are able to plot some points there. Now, if we remember that the g of x is an inverse of each other, what that would remind us is that these values are the opposites of each other. So if x were 1/4, its value would be a -2. If it was 1/2, the coordinate point on that one was a -1. And likewise, I ran out of space here, folks, sorry. 1, +1, and a 2. So 0 matches up with a 1, 1 matches up with a 2, and 2 matches up with a 4. So based off of that idea, remember, that's what inverses are. Inverses replace the x coordinate with the y and the y coordinate with the x. It moves those two around because they're inverses of each other. Graphically, do we remember what that means? Well, if we were to draw and we remember too that inverses are symmetrical about the y equals x axis. All right, that's a straight line, right? Okay, good. Let's plot some points. Let's plot f of x. So over at -2, we're up at 1/4. 1, we're at 1/2. At 0, we cross right there. Over at 1, we're up at 2. Over at 2, we're up at 4. And if we remember, we'd have an airplane taking off as such. Now let's plot the other points because they're inverses of each other. So rather than the point -2 1/4, I have the point 1/4 and -2. So 1/4 down here at -2. Over at 1/2, I'm down at -1. Over at 1, I'm at 0. Over at 2, I'm at a +1. And over at 2, over at 4, 1, 2, 3, 4, I'm at 2. And if I were to draft that, I'd have a graph that looks like that, where this is a reflection of each other about this slanted y equals x line. What can we say about the domain of this particular function, this logarithmic function? Well, its domain are all the values where I'd find an x value at. So the domain is all values greater than 0, but not including 0 because it approaches x equals 0 asymptotically. And its range are all the values that can result of that. And this looks like it goes all the way to -infinity. And this one, although it's creeping up very slowly, it is creeping up all the way to +infinity. So there's the domains and range of the standard logarithmic graph. Of course, we can transform that graph and slide that graph around, stretch it out, shrink it, and do all those types of transformations as well.